This section is on Markov processes, and let's start with an example here. I'll read it and then we'll talk about what a Markov process is. So a census study from the 1960s revealed that in the United States, 80% of the daughters of working women also work, and 30% of daughters of non-working women work. We'll summarize all this in just a minute. Assume that this trend remains unchanged from one generation to the next. Determine the corresponding transition matrix. All right, so there's a lot going on here. Let's see if we can summarize it. So from studies in the 1960s, what we had is that 80% of daughters of working women worked. All right, let's summarize this in a transition matrix. So I'm going to write this as T. I'm going to name this matrix T for transition matrix. And there's two states that we could be in. Working, not working, working, not working. So let's see what we can get here. Here's what we've got here. Here's what we know. That 80% of daughters of working women also work. Now, here's how we're going to do this. We're going to go like this. We're going this way. This is current. That's our current state. This is the next state. So we're going to go here, from here to here. So if the mother is currently working, then there's an 80% chance that the daughter will be working. So I'll put an 80% here. So I'm summarizing all this information in a transition matrix. So currently, if the mother's working, there's an 80% probability that the daughter will be working. Then, of course, that means that if the mother's working, there is a 20% chance that the daughter will not work. Now, we're also given that 30%, I'm down here, 30% of daughters of non-working women will work. All right, so now we're over in non-working women. So if the mother does not work, there's a 30% chance that the daughter will work. So currently, if the mother does not work, there's a 30% chance that the daughter will work, meaning, of course, if the mother does not work, there's a 70% chance that the daughter will not work. This matrix, T, this one here, this is called a stochastic matrix, and a stochastic matrix is any matrix that satisfies the next two conditions. First condition, first property is this. All entries in the matrix have to be between 0 and 1. And when we say between, we mean inclusive. Between 0 and 1 means it could be 0, could be 1, or anything in between. And if you look at all the entries in this matrix, it's true. They're all between 0 and 1. Now what we're getting at here is that they have to be between 0 and 1 because we want these numbers to be probabilities, right? All of these are probabilities, and of course probabilities are between 0 and 1. And the second condition, the second property, is that the sum of the entries in each column is 1. So look over here. If you add up these columns, add up the numbers in those columns, what do you get? You get 1 and you get 1. So we've got both conditions are satisfied. The entries are all between 0 and 1, and the columns add to 1, so this is a stochastic matrix. Now, it doesn't matter if it's the columns adding to 1 or the rows adding to 1. The way we're doing this is we're going up here now. We're going from a column to a row. So we're going current state to the next state. So we're doing columns to rows. If we were to do this, row to column, then we would want the rows to add up to 1. So when you look at a matrix, check to see, first of all, which way are you going? Are you going current to next, in which case the column should add to 1, or just check, are you going from row to column, in which case the rows should add up to 1. Now that 1960 census also showed this, that in the 1960s, 40% of women worked and 60% of women did not work. Let's summarize that in a matrix. I'm going to call this P. That matrix will be P, and there's two states, right? Working, not working. And what we have is that 40% were working 60% were not working. And we're going to give this a name. We're going to call this the state matrix. And I'm making it a column because our columns add to 1. The numbers in the columns add to 1, so my states are going to be written in columns. Now I'm also going to describe this right down here. I'm going to describe this as P sub 0, like at time 0, or you might think of it as an O for the original state. So the original state is this state right here. And now what we want to know is what happens in later states. So we know where you are originally. What we want to know is this. We want to know what is the state matrix for P1. Okay, that's going to be, here's the mothers, here's the daughters. And then also, what is P2? Right, we're going to get matrices for these, and we want to know what numbers to put in here for working, not working, working, not working. And then, so what we have is, right down here, here's the mothers, this is where it all starts. And we would like to know, right, if it starts off with 40, 60, what would the percentages be here for the daughters? And then for the granddaughters, and then for the great-granddaughters. And then dot, 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 just for some nth generation down here, what would these numbers here be? That's where we're headed.